So let me sort of generalize this in higher dimensions. And this is pretty important. So instead of e to the something, I'm going to use the exp notation, exponential notation, because it's sort of nicer. We have 2 pi nx over L as sort of one spatial dependence, and you multiplying that because we don't just have x now, we have x, y, and z. So let's say we're talking of 3 dimensions. And notice that I'm using m here because these numbers have to be independent of each other. So 2 pi p z over L. So we can sort of combine them together to have I k sub x of x plus k sub y of y plus k sub z of z. And because we're defining a vector k to have components kx, ki, kz, this is the wave vector, points in the direction of propagation of wave. That's sort of an easy derivation because we know what the position vector is. It's x, y, z. So what we have inside just becomes I times k but dotted with r. You can work this out, it's simple. Right? So now our Fourier transform will give us a function of k which is different from small f, which is a function of the position vector. We're going to have 1 over square root of 2 pi, but this was for one dimension. We have, say, n of these. So to raise to the nth power, integral from minus infinity to infinity, f of r, that's the position vector, e to the negative I, k dot r. I use the simpler three-dimensional example because we can generalize this approach. Here our vector has 3 components. In n dimension it will have n components. Same thing with the position vector. Scalar integral over the entire space. So this is going to be dx, dy, dz in Cartesian, say for 3 dimensions, but dx1, dx2 till dxn for n dimensions in Cartesian. I'm having these sort of magnitudes because for, say, polar coordinates, you need to worry about the scaling factors or the differential volumes that change. The more useful version of this is a Fourier transform over both space and time. So in which case you have n plus 1. Many textbooks omit this or sort of have a weird factor. The factor doesn't really matter. It depends on what author you use or read from. All that matters is the k dot r. Let me do a better job of writing that. Minus omega t. Now this form, we have a minus because this entire thing is the plane wave form, or the functional part of the solution to the wave equation in n dimensions. Forward moving wave will have a minus between the position and the time parts. A backward moving wave will have a plus there. So what we're essentially trying to do is we're trying to represent, at least if we sort of try to find this coefficient, is we're trying to represent this initial waveform or time form, because it's space-time, as a weighted coefficient of these plane wave solutions. So this is your weighted coefficient, and this weighted coefficient will, sort of be the perfect one over the entire interval because we remove periodicity in the continuum. So this weighted coefficient, along with this, you integrate them out, you're going to get f of r comma t, because that's just the inverse Fourier transform. So the inverse Fourier transform is basically representing f of t, r comma t in this case, as linear combinations of this weight that we found and the plane wave solution. And this linear combination, since you're working on an infinite dimensional basis, instead of a sum, we have an integral over the entire space. In this case, it's sort of space and time. I probably need to like specify this. So this is for the time. So for the space, we just have the same factor, and for time we have dt going from 0 to infinity. These things are really useful. My research in plasma waves right now is pretty heavily uses this stuff to basically convert simple differential equations, or not so simple differential equations, into simple algebra or linear algebra, which can be done easily. That's why this is useful. So let me just sort of give an example, a very good example, which is a relevant example in terms of quantum mechanics. So in quantum mechanics, we have the correspondence principle, which says that basically like stuff has wave-like behavior and particle-like behavior. Wave-like behavior is a collective behavior because a wave is sort of a collection of different particles moving in a certain way. But the way that collection of particles or probabilities, that's what the interpretation of quantum mechanics is. This collection of probabilistic, I did a horrible job of spelling that. Trajectories should like correspond to what happens classically. So if you're passing an electron through a slit and observation happens, then like it's gonna behave in a classical manner. So it should sort of like correspond to classical behavior in some way. Now the one way to like sort of deal with this necessity condition is have a wave packet. So what happens is if you take waves and you superimpose them on each other, say something like but the summation or the indexing is happening on the k variable because omega is a function of k by dispersion relationship. That's how frequency changes as a function of k in some medium. So it's specific to a medium. In vacuum, for light, this will just be c times k. And then we're gonna sum that because it's going to, if we do a superposition of waves with different k, so it's going to be a summation, since it's continuous, integration over k with some weighting function from say minus infinity to infinity, and that will give us our wave packet. So wave packet is something, a wave packet is something that is basically after you superimpose all these things, you get this red stuff. But I mean, whatever, I mean, why do you care about the red stuff is because if you sort of say the envelope function that I've given in green here, the red waves may sort of move in a complicated, crazy way, but this green envelope function moves in a nice predefined way. So the velocity of this green envelope function is the classical velocity, and this sort of uncertain varying velocity is what is sort of like is a measure of the probabilistic velocity of what the electron will do. So this makes sense for this quantumness or uncertainty, and this makes sense for the correspondence because it should behave like it does classically. So you can reason with quantum mechanics that it's the wave packet that's behaving classically. And if you sort of shrink down this wave packet width, it becomes a delta function, and that's pure classical. So for large particles, this wave packet, like a bowling ball or something, this wave packet is so narrow that you don't actually notice these uncertain or collection of probabilistic things at all. So notice this looks like an inverse Fourier transform, and it should, because again there's a k integration going on, and we have an x and t here. There's no time integration as such. We're leaving that sort of independent for now. So say someone told us what the weighting function is for superimposition of plane wave solutions. They told us it's 1 over square root of 2 pi sigma squared over pi 1/4 e to the negative sigma squared k minus k naught squared over 2. So with all of that, we can just plug that in because we need to solve for the wave packet. Integral from minus infinity to infinity dk. We're working one dimension, so just forget the other bits. Sigma squared over pi to the 1/4 e to the negative sigma squared k minus k naught squared over 2 e to the I kx minus omega k was ck for vacuum. So the phase velocity is the ratio of omega and k is equal to c. So that's why you have this. The phase velocity is what this green packet travels with. The group velocity is what, sorry, the phase velocity is what this red bunch travels with, which what each particle will travel at inside, governed by this like random red bunch. The group velocity is what this wave packet travels at. So the group velocity should correspond to the classical velocity. We don't really care much about the phase velocity because in a light wave the phase velocity can be greater, but the group velocity is always less than the or equal to the speed of light. At least in vacuum it is equal to. In other media it has to be less than. So the information travels at the group velocity because information that's complicated is in a wave packet like this. So we really care about the velocity of the wave packet and not each individual particle speed. Anyways, much said. We have this bit here. Let me just redefine this. Sigma k minus k naught over root 2. That's u. So, k is square root 2u over sigma plus k naught. Du is sigma over root 2 dk. So minus infinity to infinity square root 2 over sigma du over root 2 pi sigma squared over pi 1/4 e to the negative u squared e to the I. I'm just sort of beast mode this integral. This is just substitution and algebra going on at this point. And now the best way to solve an integral that's complicated in this way is to complete the square. Notice I'm sort of grouping the factor of pi. E to the negative u squared minus I, I'm dividing by 2, square root 2 over sigma x minus ct times u. But if I sort of wait, we should, never mind, I'll do it step by step. See, remember, see, the last term can be taken out. It does not depend on u at all. E to the I k naught x minus ct minus infinity to infinity du over pi cube sigma squared to the 1/4. E to the negative, complete the square. Now we divide by 2. The division of 2 did not happen there, my bad. Over square root of 2 sigma squared. But if you do this square, you are going to have this term generated by this last factor, which is going to be positive because I squared is negative with a negative is positive. So we'll have to tag along a negative to cancel out that term. So the square of that term, so square over 2 sigma square. Again, this does not depend on u, so can be taken out. So e to the I k naught x minus c. This is actually a lot to write, lots of pen work. That's just the annoying bit about quantum, really. Atrociously long, big, annoying terms. So du over pi cube sigma squared 1/4 e to the negative u minus I x minus ct over root 2 sigma squared. And one interesting identity or formula. So if you have a Gaussian, complete Gaussian on the entire interval, but offset by this imaginary factor, that's still going to be equal square root of pi, as if it were the Gaussian that weren't offset, or if it were the real Gaussian. It's an interesting thing you can prove with complex analysis. It's pretty easy. The contour you can sort of use is one that has this offset factor in it, and then show that the entire contour integral is 0. So the real part equals whatever happened on the top part. Anyways, yeah, I'm just thinking out loud here. So this guy just becomes square root of pi, and that's really nice because we can completely simplify this thing. Completely simplify this to be square root of pi divided by pi to the 3/4 root sigma so the wave packet is just finally, let me just write the algebra again. The 4th root of pi sigma squared in the denominator, negative e to the negative x minus ct squared over 2 sigma squared e to the I k naught x minus ct. And this of course is for a photon or light, because we have this c from the dispersion relationship. For other complicated stuff, you'll have to use Planck's equation, photoelectric formula, or just this relationship and how that relates to momentum, say. And it gets uglier, but this is nice. One useful thing to note here is that if you say set k naught to 0, this goes to 1, and if you're working in the wave packet reference frame. X minus ct just becomes the x prime in that frame. And then if you tune these factors right, all these factors, if you like say set them such that this guy becomes 1 or in some way, you're going to notice that what we started with was a Gaussian in the k space, because now we're setting k naught to 0, so we just have k squared. Which becomes a Gaussian in this wave packet frame. So the Gaussian becomes a Gaussian over the transformation. So one way to put it is a Gaussian is an eigenfunction of the Fourier transform operator. Or in this case, it was the inverse Fourier transform, but this stuff is analogous, interchangeable. And the basis we're using was, of course, for the L squared space, which is a Hilbert space. Actually, I can make another video to show that it is. So, well-defined norm, all those metric space, Cauchy sequence converges and stuff like that. It is a linear operator because you can check for linearity, and that's why this eigenfunction eigenvalue analysis or analogy works. This is linear as long as this is functions are of this form, and they are, because square integrable Hilbert space, that's what we use in quantum. We need a Hilbert space. These functions are pretty well behaved under integration, so that makes Fourier transform and the inverse Fourier transform, the pair operations, linear operators. Boundedness is another question that depends. Well, the absolute value squared of this is sort of the probability. If you integrate it out, that has to be 1, so it's bounded in that sense. But again, this stuff gets complicated, but you can think of this as a linear integral operator. And that's pretty much for this video. Extremely long, I'm sorry about that, but lots of interesting juicy stuff. Like and subscribe to my channel, guys. Recommend me to your friends, spread the word of gamma di gamma. See you in the meantime. Go on a hot date somewhere. It's Valentine's Day, for God's sake. And peace out.